So this is the rolling motion of a cylinder, and these are the 4 points that we have taken on the cylinder, and we have drawn the velocities at that particular point. So you can see that we have not drawn any arrow at P3. So it means I have not drawn any arrow because the velocity at P3 is 0 at a particular instant. So these are the velocities at a particular time, at a particular instant of time. So the velocity of the point of contact P3 is 0 at any particular instant. When the cylinder rolls without slipping, so it is not, there is no slipping, but it is only rolling. So rolling motion has 2 motions, translational as well as rotational. Now if you look at so open your NCERT book, students. It's page 173. We'll read from book also. So one of the most common motions observed in daily life is the rolling motion. All the wheels used in the transportation have rolling motion. For specificness, we shall begin with the case of a disc, but the result will apply to any rolling body on a level surface. So we are taking this case of disc, which is figure 7.37, and then we'll do one example, so where the same case will be applied to other bodies also. But here the important thing is that we are assuming that this disc is moving without slipping. So what does this mean, moving without slipping? That at any instant the bottom of the disc, which is in contact with the surface, like here it was P3, here the point is P0. So this point in contact with the surface is at rest. So without slipping means the bottom of the disc, the point at the bottom of the disc is at rest. So point of contact at rest for a particular moment, okay, at any instant of time. So of course this point of contact keeps on changing. This point contact, and next moment this point will be the point of contact, next moment this moment. So as this point reach here, at that particular point that point of contact will be at rest at that particular moment till it is in contact. Now we can we have remarked earlier that rotational motion is combination of translational and rotational. So we know that in translational motion of a system of particles is the motion of the center of mass. So what do we consider in translation motion? Motion of the center of mass. So what is center of mass? Like we have studied that on this particle, this mass particle, and force F is applied on this particle, and this particle will accelerate. If this has mass m, then it will accelerate with the acceleration a. So force is equal to mass into acceleration. But suppose you have this whole body and you have applied the force. Now as you have studied that different motion, different particles have different velocities, linear velocity, and different acceleration also. So whose acceleration you are going to take? So this is the mass of the body, that so F is equals to this mass of this body, but whose acceleration you are going to take? So we have a point that is center of mass C. So this body is actually equivalent to, you can assume that the whole mass of the body is concentrated at a point, that is point C. So this C point, this is a mass object, and it has the mass m, the center of mass. So assume a point object which has mass m, and this force is acting on it. So these two cases are similar. Okay, so we write with capital A. So that's the difference. Here it is for a particle, mass particle we are considering, and here we are considering extended body, rigid body. And we are assuming that rigid body, when we apply an external force on it, then we assume that the whole mass is concentrated at the center of mass, and that force is applied at the center of mass. So this capital letters, this capital A tells you that this is the acceleration of the center of mass, and we are writing it for extended rigid body. So even if you have not attended earlier classes, doesn't matter. Just think that this is what I am telling you, and attend the it's must to attend NCERT solution exercise today. So the whole chapter is going to revise. Okay, still it is sort of revision going on. Okay, now so in translation motion we study the motion of the center of mass. So if it is acceleration, it is acceleration of the center of mass. If it is velocity, it is the velocity of the center of mass. So you write it with capital V, or you can also write it with the velocity of the center of mass as this small velocity, small v, but along with it you need to write Cm. So Cm is the center of mass. Okay, so if you look at the definition of center of mass, what it is written in your body, written in your book. So it is on page 178. Center of mass of a system of particles moves. So this center of mass moves. So this belongs to a center, the center of mass is always a system of particles, and this system of particles has a point which is C, where we assume that whole mass is considered, and center of mass move as if all the mass of the system is concentrated, like I've shown you here in this figure, that this is equivalent to, this extended body is equivalent to, if force is applied on it, you can assume that the whole force is applied on the center of mass, and you will be studying the motion of the center of mass only. It's concentrated at center of mass, and all external forces are applied at center of mass. Okay, so this is at page 148, and this is the equation 7.11 equation. Okay, now So it means this is your extended body, the disk. This is your rigid body, and we will be studying the motion of the center of mass. So in the formulas, the velocity, acceleration, whose velocity, whose acceleration we are going to take, that we are going to take of center of mass. Okay. Now let the velocity of center of mass v, let velocity of, so I am reading from the NCERT, let velocity of center of mass is equals to VCM. So students, I am writing it slowly so that you can also write along with me. Okay, so keep on making notes along with me with understanding, and if there is anything you are not understanding, please ask it. Okay, so this is the VCM, is the velocity of the center of mass, and therefore the translation velocity of the disk. So this is also the translational velocity of the disk. So where will we have the center of mass? So of course this is a symmetric body, and the center of mass will lie at the geometric center of the disk. So VCM is the velocity of C. So VCM is the velocity of C, means the geometric center of the disk. And you can see that this velocity, this VCM, it is parallel to the level surface. So this is your level surface, and this velocity, you can see that this is parallel to the level surface. Now the rotational motion of the disk is about its symmetric axis. So the axis is passing through this point C, and it is perpendicular to the plane of the book, or the plane of the screen, or the plane of the paper where you have drawn this figure. So this is my level surface, and this point is the geometric center of this disk, and this is the velocity of the center of mass, which is, so always keep in mind that this is the magnitude and this is the direction of the velocity of the center of mass. So that's what we do with vectors. And this is the rotational motion of the disk about the symmetric axis passing through point C. Thus the velocity at any point of the disk, so we have taken different points, like this point is this is touching, of course, this surface. So this point is P0. So this is your surface. This point is P0, and we have taken another point that is over here, that is P1, and we have taken another point where that is P2. So the velocity at any point of the disk, like at point P0, P1 or P2, it will consist of two parts. One which is translational velocity, that is velocity of the center of mass, and another one is the linear velocity on the account of rotation. So due to rotation, we have the velocity, that is velocity due to rotation, and due to translation we will have the velocity VCM. Okay, so that's the translation velocity, and that's the linear velocity. So this one is linear velocity, this is translational velocity. Now, what will be the magnitude of this VR? So magnitude of this VR, you can write it like this or like this. That's equals to R into omega. So omega is the angular velocity, angular speed here. I have written, if I am writing it, magnitude, and the formula is, if you write the formula of this velocity, that is equals to omega cross R. So we don't need this, but we get this formula from there. So VR is equals to R omega, where omega is the angular velocity of the rotation of the disk about the axis, and that angular velocity depends on the how much this angle is rotated with respect to the time, and this angular velocity is same for all the points of the body. So that's the case. So angular velocity is same for all the points of the disk. So where omega is the angular velocity of the rotation of the disk about the axis, and R is the distance of the point from the axis of rotation, that is from C. So suppose if this is the point you are taking, you want to find VR at this point P2. So this will be your distance R from the axis of rotation, and so this will be your R, and then omega is same for all the points. So R multiply omega, you will get the VR. So VR can be drawn over here. So where is VR? VR is, suppose in this direction, that's your VR, and where is the velocity or the translation velocity will be parallel. So this is velocity of translation velocity here at this point. So that's this point P2. Okay, so this is your translation velocity, this is the velocity, sorry, this VR is your linear velocity, that is your rotational part. So this VR is your rotational part, and this VCM is your translational part. So what will be the velocity at this point? So we will take the vector addition and we'll draw the parallelogram. So here also in this figure you can see that, complete this parallelogram, and you will get V2. Okay, so that's the V2, which is equals to VR, that is a rotational part due to linear velocity due to rotation, and translational velocity plus that is your velocity of the center of mass. Okay, so velocity of the center of mass is same for all the points at a particular instant. So the velocity, you can see that the velocity VR is directed perpendicular to the radial vector. So this VR is perpendicular to this radial vector. So this radial vector, this is perpendicular. So this angle is, you can see this angle is 90 degree drawn. So this is the angle between R2 and VR. So this is VR. Okay, this is VCM, this one, this is your VCM, and that's your VR. So this is your V2, which is the sum of VR and VC. Okay. Now the velocity of the point P2, that is V2, and its component VR and VCM are shown in the figure now. So VR is perpendicular to CP2, VR is perpendicular to it, okay. Now it is easy to show that VZ is perpendicular to the line P0, P2. So of course VZ will be, means this is the axis of rotation. So VZ is perpendicular to the plane of this disk. So of course, and P0, P2 is the line on this plane, and axis of rotation is perpendicular to this plane, passing through the point C. You can assume, you can visualize. So therefore the line passing through P0 and parallel to omega is called the instantaneous axis of rotation. So that's the instantaneous axis of rotation passing through P0. So at this particular instant, the line passing through P0 and which is parallel to the direction of the angular velocity. So this body, the rotation is in this direction. But what is the direction of this angular velocity? What is the direction of this angular velocity? That's another important point. So what is the direction of this angular velocity? Yes. So this is XY plane that I have drawn, and Z axis, you can see that it is perpendicular to this plane passing through point C. So what is the direction of angular velocity? So direction of angular velocity, for that, students, you can see figure 7.17a, that figure. So if so it is just like you can hold this means the fingers of your right hand in the direction of the motion. So how will you curl your fingers? So put your fingers on this, put the fingers of your right hand on this, in this direction, okay. So your fingers are pointing in this direction, your finger, okay. So put your fingers, can you put your fingers like this? Yes. So where is the direction of your thumb? Tell me. If you put your fingers, your thumb is supposed to be perpendicular to the fingers, okay. Hold your thumb perpendicular to your fingers and put your fingers in this direction, okay. So where will your thumb be pointing? Your thumb will be pointing, yes, outward,
into the plane.
into the plane, yes, good. So it is pointing into the plane of the paper. Your thumb is pointing, and that is the direction of your angular velocity, okay. So means and how do we show it? So we show it like this. So it is into the plane of the paper. That is the direction of angular velocity. So this is the direction of the rotation, which is clockwise. And if you curl your fingers over here, so your thumb will be pointing into the plane of the paper, and that is the direction of the angular velocity. You have seen the figure also, students? 7.17. Yes. Any doubt? Noted it down? Yes?
Yes.
Good. Let me show you this figure also. So in this figure, you can see that this is the this is the direction of rotation. Suppose if the disk is rotating in this direction, that's clockwise direction. You can see. So it is going into the plane of the paper. The direction, and here the direction is anti-clockwise. The rotational motion is anti-clockwise, direction of rotation. So hold your fingers. Now hold your fingers like this. So you can see where your thumb is pointing. Yes, where your thumb is pointing. So this is your thumb pointing, and you are curling your fingers like this of your right hand. Your thumb is supposed to be perpendicular with the fingers, and here the thumb is pointing outwards, out of the plane of the paper. So we can also show out of the plane of the paper if there is an arrow. So if the arrow is coming, you can see it is coming towards you. So what the arrow will look like? It's the point that will look at you. So that's another way to tell you the direction. So this point, circle, and this point at the center. So it means that it is the direction of the vector is coming out of the plane of the paper. And if it is going into the plane of the paper, what you will see? There is a cross at the end of the arrow. This is what you will see if it is going inside. So then you will see this cross. So that's the meaning of. So that's how we draw the direction. If it is, you can see this arrow, back of the arrow. So it means this arrow is moving into the plane of the paper. Here you see the tip of the arrow. So it is coming out of the plane of the paper. So now at P naught, the linear velocity VR, due to the, of course this VR is due to the rotational motion, is directed, this VR is directed exactly opposite to the translational velocity VCM at P naught. So at P naught, so definitely we have both the velocities. So at V naught, this is my VCM. Okay, this VCM, translational velocity due to translation motion, and at this point I have the rotational velocity. So rotation is in this direction, you can see. Yes, so I have this rotational velocity, means velocity due to rotation, that I call linear velocity. So students, I have written both the things over here. Okay, so this is your linear velocity, this is your translation velocity. So they are equal and opposite. So what will be the resultant? So VR is equals to minus VCM, okay, at P naught. So what will be the net velocity? So both have the same magnitude. So their magnitude is equals to the same. You have written it over here. So the magnitude is same. So magnitude of the magnitude means VR is equals to VCM, and that's equals to R omega. So the magnitude is same, but direction is opposite. So that's how we write them. Okay. So what will be the net velocity at this point? So net velocity at this point P naught will be 0, because adding the velocity, so velocity at P naught will be, you will be adding these two velocity. So VR plus VCM that are exactly equal and opposite. So the velocity at P naught is 0. So that is why we see that the point of contact P naught of the disk with the surface is at rest. Okay? At any particular instant. So that can only possible when there is rolling motion without slipping. So the center of mass of the disk moves with the velocity Vcm, and the disk rotates with the angular velocity omega with its axis that is passing through C. Vcm is equals to r omega, where r is the radius of the disk. So incidentally, this means that the velocity of point P1, which is at the top. Now what will be the velocity at point P1, which is at the top? So at P1, so the point of contact, and this point is at the top, just opposite to point P naught, this point at the top of the disk. So its velocity we can write as V1. So at the top its velocity is written by V1. So what will be the magnitude of V1? You can clearly see here that this is your VCM, and now it is also rotating, so this VR, this will also be here. So this is VCM and VR. So here both of them are in same direction. Okay, so if they are in same direction, these two vectors, they will be added. So you can see that this is VCM, their magnitude are added in the same direction. So if this is just like you are applying 2 Newton force in this direction, and again one more person is applying 4 Newton force in this direction, or 2 Newton, both of you are applying. So you have a, suppose, box over here, and you are applying 2 Newton and 2 Newton force. So what will the net force? So net force will be, you will be adding this, so this magnitude and this magnitude, so, and the direction will be the same. So 2 plus 2 is 4 Newton in this direction. So that's the same case. VCM and VCR, here they were in the opposite direction, but here they are in same direction. So you will be simply adding VR plus VCM at this particular point at the top. They will be added, so their magnitude will be, so they are equal and opposite, equal and in the same direction. So they are equal. So equal means a vector is equal means same magnitude and same direction. So you can write it as this or this, right? So this V1 is twice of this velocity, and magnitude you can write as 2 VR, okay, or 2 VCM. Now what is your VR and VCM? That magnitude is R omega, so that will be equals to 2 into R into omega. So that's the velocity at the top. And what will be the direction of this velocity? Direction, you can see it is parallel to the surface, because the direction of VCM is parallel to the surface, so it is same as VCM. So this condition is applied to all the bodies, all the rolling bodies. Okay, now our next topic, that is let us find the, so we have understood the rolling motion. Any doubts, students, till now? So we have just done the terminology, okay, with these two velocities, and we have found the velocities at the contact point of contact and then at the top. Okay. Now So kinetic energy of the rolling motion, that's our next topic. So now our next task will be to obtain an expression for the kinetic energy of the rolling body. So we'll derive the formula for this. What's the formula? The kinetic energy of the rolling body can be separated into the kinetic energy of translation plus kinetic energy of rotation. So this kinetic energy of the rolling motion is equals to kinetic energy of translation plus kinetic energy of rotation. So we are taking a special case here. This is a special case of a general result for system of particles, according to which the kinetic energy of the system of particles, that is K, is separated into the kinetic energy of the motion of the center of mass. So it's motion of the center of mass. So here we study motion of center of mass. So this kinetic energy of translation, we write it as half mv square. So I told you with capital letters. So we are writing the magnitude, and you know that v dot v is v square. So plus kinetic energy of the rotational motion about the center of mass. So that will be writing as a k dash. Okay, so that's my total kinetic energy of the system of the particles. Okay, now we assume this general result and apply it to the case of rolling motion. Okay, so here in the book they have written k is equals to this k dash earlier plus half mv square later. So let us write it in the same format as it is written in the book. Okay, so here the kinetic energy of the center of mass. So this is the kinetic energy of the center of mass. This capital V is telling you that this is for the center of mass kinetic energy. That is the kinetic energy of the translation of the rolling body is, you can write it like this, or you can also write it like k is equals to k dash plus half into m into. So now you are assuming that whole mass is concentrated as the center of mass. So now we are assuming this whole extended body. So here we were assuming it as whole extended body and with the mass m, and the velocity of this was suppose center of mass. So the velocity of this center of mass was v. Now we are considering it as equivalent to that this whole mass of this body is concentrated at point C. So now we are treating it as mass particle, point mass. So, and it has the same velocity, that is instead of writing it capital V, we are writing it VCM. So velocity of this center of mass, so equivalent to this extended body, this mass, and it has the same mass. So this capital M I am replacing because I am now considering it as point mass particle, so writing it as small m. So this capital M is same as small m, and this V is same as this. So notation is different. So where V is the mass of the body, so this M is the mass of the body, but notation is different because we are considering it as point mass. The whole mass of the body is concentrated at this point. and this VCM is the center of mass velocity. So velocity of this particle. Okay. Since the motion of the rolling body is about the center of mass, is rotation, so it's a body is rotating about the center of the mass. So we are writing this K dash. It represents the kinetic energy of the rotation of the body. So how do we write it? So K is equals to, so students just understand here that I have this formula that was kinetic energy equals to half mv square. This is what you used to write. Now for center of mass, if I am writing, I will write this formula as for system of particles. So K is equals to half m v square. But now I'm considering this extended body concentrated at this point C. So again I have went back to this is point mass. Okay, so here this is extended body, this formula, and I'm going back now to point mass. So I'm assuming that this whole mass of the body, which is capital M, and this velocity was of the velocity of the center of mass. So this whole body is concentrated at center of mass. So I will be writing this formula for the center of mass for the again for this like point mass. So I will be rewriting it as m v cm. So now here this v and this vcm is the difference. So with this v is your original is the particle. See, so that's your so we have even exercise question 3.1 where you are supposed to tell that which one is point object. So here we are treating as we have studied up to chapter 6 all the objects as point objects, but in chapter 7 we have introduced the concept of extended body. Means lot of mass, a lot of point objects are there in this extended body. So now, but when we are studying the motion of the extended body, how we are going to study the motion? So we are studying the motion of the center of mass, where we assume that the whole mass is concentrated. So here we are assuming this, and we are writing this formula. So this is for the extended body, and this is for the point object. Now next is the formula for, so this is due to the translation motion and due to rotation motion. So kinetic energy due to the rotation, so kinetic energy of a rolling body. So kinetic energy of rolling body. So here it is, this is translational motion. And so now for the rolling body, see what variables we will have. I will write it as K dash. So this is half. Now instead of mass, I have the I, which is moment of inertia. So it has the same role as mass. So what is the role of mass? If you have a heavy truck and if you have a small car, where so its mass is suppose 2000 kg, its mass is 600 kilogram, its mass is around 5000 kg. So where do you need, both are at rest, where do you need to apply more force so that they will be in motion? So of course you need to apply more force at the truck. Why? Because truck has more mass. So more mass means more inertia. That is Newton's first law. So it is that. So if they will start moving, and now you want them to bring at rest, so you need to apply force in the opposite direction. So where you need to apply more force? So of course in case of truck also you need to apply more force. So more is the inertia, more is the force required to bring the change in the state of the motion of the body in translation motion. But if I am rotating the body, so in case of rotational motion, so rolling body, this is for the rolling. So rolling is rotation and translation. So let us write for rotation here, not rolling, rotation. So kinetic energy due to rotational motion will be, so what role does play? So I want to rotate this rod. So one is, suppose this rod has mass 1 kg and another has mass 5 kg. So which one will be easier to rotate? So of course this one, so it is rotating like this, so of course it is easier to rotate this one. Or you can say, we can take the case of the disc. So if it is a ring, so first you can see it depends on the mass. So more is the mass, so this moment of inertia, it depends on mass. Okay, now what's the second thing it depends on? Let us see that we have a ring and we have a disc. So we have a ring and we have a disc. So this is my so I have kept it in the plane of the paper, this ring and this disc also, and I want to rotate it. It will remain at its same point, this point will remain at its same point, but I want to rotate this. So this will be my axis of rotation. So where do I need to apply more force? So here force also torque, actually rotational force is your torque. So where do I need to apply more torque? In which case? So here also it was torque, this rotational force, the force responsible for the rotational motion. So where do I need to apply more torque? So you can see that I form a couple, I apply, like when you open the cap of a bottle, so you apply the force in the opposite direction. So if, like here you are holding it, your thumb, so you are opening up, so here you are applying the force in this direction at this point, and here you are applying the force in this direction at this point. So equal and opposite forces, they form a couple along different line of action, and as a result there will be the rotational motion of this ring. So ring also you can you apply force here, so fingers over here, thumb over here, and it will rotate at that point. Ring, yes, put this ring on your table and you can rotate it. Now you put a disc, okay, and rotate it. So where do you need to apply more force, friends? In case of ring or in case of disc? This force that you are applying here and here, yes? So it's proportional to mass, but it also depends on the distribution of mass. So along with mass, it depends on how your mass is distributed. So if the mass is away from the axis of rotation, you need to apply more force. So you can see here the mass is far away from this axis of rotation. So it looks like, so don't get it confused with the truck and the car, that it has more mass, it has less mass. But I am assuming here that both have same mass. If this has 5 kg, this also has 5 kg. Of course the ring doesn't is not of 5 kg. So suppose, but the masses are same. Okay, so this very heavy ring, suppose 1 kg, and this is, so I'm not talking about golden ring, of course. So this steel ring, so it has mass 1 kg, and this also has mass 1 kg. So look here where the whole 1 kg mass is. It is all there on the ring, which is far away from the sector of the axis of rotation at a distance r. But here the mass is spread, and so much mass means mass is near to the axis of the rotation. So if mass is near to the axis of rotation, it is easier to rotate it, and it will have lesser moment of inertia. So this moment of inertia is also directly proportional to this even r square of the distance that this mass is, this particle is away from the axis of rotation. So this weightage is square. So but their mass is same. So mass is not going to impact because mass is same. Now the only thing that is going to impact is the how much is that mass spread and away from the axis of rotation. So here it is near to the axis of rotation. It is easier to rotate this body. So this body is easier to rotate, so it will have less moment of inertia. So the formula, I'm not driving here, but just it was a discussion to just get you familiar with the moment of inertia. So here the moment of inertia of the ring is mr square, that is given in the table 7.1, and the moment of inertia for the disk will be, actually it is for this disk, it will be half of the inertia, moment of inertia for the rotational motion in case of ring. So in case of ring it is mr square, and in case of disk it is mr square by 2, because in disk the mass is spread near to the axis of rotation. So this moment of inertia plays the same role as mass in translational motion. It doesn't allow the body to rotate, and if the body is rotating, it doesn't want the body to stop the rotational motion. Okay. So for mass, we have instead of mass in rotational motion, we have moment of inertia, and instead of this linear velocity, we have the angular velocity. So these are the three things this we have studied till chapter 6, and this is in chapter 7, extended body. So writing this formula and writing this formula, and then for rotational motion it's equivalent to this translational motion, this linear motion. You can call it linear, you can call it translational. Okay. And now for the rotational motion we have this formula. So m is replaced with I, so same role that mass is playing in the linear motion, here moment of inertia plays that role. But the difference is that here mass is directly you need not to find the mass, means mass is like, there's no formula for the mass. So mass is just the matter contained in the body. So but here this I, you can see that it will be different for different bodies. So this I will be different for different bodies, even if they have same mass. Okay, even if the bodies have same mass, but like for the ring and disk, they have the same mass, but their moment of inertia is different, because mass is distributed in the different manner. Now if you take the case of the ring, instead of so here the ring, you placed it on the table horizontally, so here ring was horizontal position. Now place your ring in the vertical position, place your ring vertically, and this is the axis of rotation through the diameter, and it is you can see, means parallel to the surface. This axis is parallel to this surface. So this is your surface, so this is parallel to the surface, this is vertical. Now rotate this ring. Okay, in the same way, if you rotate this ring, you need to apply that, so it will have the lesser. So some of the time, so here you can understand that this motion is different as compared to this. So here you are applying the torque, force in this direction, force in this direction, but here you are actually applying the force here into the plane of the paper. So that's into the plane of the paper you are applying the force, and here you are applying the force out of the plane of the paper. So also you can say sort of torque here. So here your fingers, like here this force was vertically upward and this force was vertically downward. So here also this force is into the plane of the paper and this force is out of the plane of the paper, and this will rotate. Some of the time we have these kind of toys also. There's some rod in the middle and there's ring, and that is rotating. So but here the moment of inertia was mr square, but in this case the moment of inertia will be lesser, that is mr square by 2. So students, understand this concept. Same ring, same mass, but you have changed the axis of rotation. So you have changed the axis of rotation. So you see that here this axis of rotation is passing through the ring. Okay, one of the diameters of the ring, this axis. So along the diameter, this so this mass is near to the axis of rotation. You can see this mass is near to the axis of rotation. Here all the mass was at a distance r from the axis of rotation, but here see this is near, this is near, this is near. So the mass distribution has changed due to change in axis of rotation. So mass distribution from the axis of rotation is changed, so moment of inertia will also change. So moment of inertia depends on how the mass is distributed. So even if the mass is distributed along the around the axis of rotation, so even if the ring is same, so look at this table. Even if your ring is same with the same mass, so all these bodies have same mass m. Okay, all the bodies have same mass m. But the axis of rotation is different. So here both are ring, both have same radius r, but you can see that their moment of inertia is, so moment of inertia of the ring. So you need to, so important here is the axis. So body and then axis. If you change the axis of rotation, the moment of inertia will be changed. It will be easier or difficult to rotate the body. Okay, if you change the axis, and if it is moving, then it's easy or difficult to stop that rotational motion. The force that you are going to apply will be different in both the cases. So as the mass, the role of mass was playing the role in linear motion, so moment of inertia is playing same role. So in case of disk, so this is in case of rod. If you are rotating this rod, this is ml square by 12 moment of inertia with the rod of length L. And if you are rotating like this, so here also it was half became half. So if you rotate the disk along its diameter, then along so half of mr square by 2. So already it was mr square by 2 and half of it mr square by 4. Students, I am just telling you the way how to remember these formulas. I am not deriving this formula. This is not derivation. Okay, so this is not derivation. Derivation is different thing. We have done it in I think in video number 22 or so, where I have written theorem of parallel and perpendicular axis. So see that video if you want to know more about moment of inertia. I think those who have not seen it, see the videos of moment of inertia and then the theorem of parallel and perpendicular axis. The video I think from 21 onwards we have those videos. So how these formulas are derived. So I'm just giving you a simple idea. And now in case of cylinder, it is mr square by mr square. So if this is the axis of rotation, which is this you can see, but if this was hollow cylinder, so if the cylinder is solid, then again the moment of inertia is decreased by half, like in case of this ring which was hollow and this filled disc. Okay, so you can remember. And what about this solid sphere with radius r? Its moment of inertia is mr square by 5, 2 by 5 mr square. So students, we were at this point. So like this formula we were writing, the kinetic energy of the rotational motion is means here this mass is replaced with moment of inertia, and moment of inertia have different formulas. Even for the same body, if the axis is different, we have different formula. And this, instead of this linear velocity, I have this angular velocity. So angular velocity is like the particle is at this point and then it has moved from this point to this point, this angle theta. We have done it in circular motion also, I think in last topic of chapter number 4. So there also we write the angular velocity, that is equals to change in this angle, that is delta theta, suppose. And if this is if theta naught is 0, we simply write it as theta divided by t. Okay, so now we have written. So main thing is that what we are writing, kinetic energy of the rolling body in the rolling motion will be equals to kinetic energy due to rotational motion plus kinetic energy due to translational motion. Okay, so kinetic energy due to rotational motion is we have written it as half moment of inertia into omega square, and here it is half into m into VCM square. So this plus this. Now we are substituting this moment of inertia with so students, this mr square, okay, in all the formulas you see that the length is means the r, you will find it r square, so we can write this moment of inertia also as ml square. Okay, so L mk square, so mk square, k is the radius of gyration, so k will be different of course for all these bodies. So write it mr square is equals to mk square. So what is the value of k here? So k in this case will be r. Okay, what is the k in this case? Mk square. So what is the k in this case? So you can see that k square is equals to 2 by 5 r square. Okay, comparing these two, m will cancel out and k will be equals to under the root 2 by 5 r. So this k is radius of gyration. Okay, so we can write this I as mk square. So this k will definitely be different for different bodies. So that's written as half m k square and so that's the value of I have written for this I, and now what will be the value of VCM? So what will the value of VCM is equals to, the linear velocity is equals to r omega. So here this r is we are taking the disk, so here r we are taking this capital R, so VCM is equals to r omega, and putting these values here, so what do we get? So let us write them in the form of VCM. So omega is equals to VCM upon R, right? So this is VCM upon R square. So simply putting these values of this omega and value of I, that is equals to mk square. So I can write it as mk square in all the cases. The k is radius of gyration. Okay, that's plus half m VCM square. So kinetic energy of the rolling body, what do I have here? Half, so this is m into k square, and this is VCM square upon r square plus half m VCM square. And further I can take this half m VCM common, and we will get as 1 plus k square by r square. So this simple, this step even you need not to write, you can directly get the common this. So only 3 steps. So this step 1, step 2, and this you can write step 3. So only 3-step derivation of the kinetic energy of the rolling body. Okay, So I hope this is clear. So students, just practice this whatever we have done. Just read it out. I know that this is very heavy stuff for the students who are watching it for the first time, but rewrite it again. Just go back to the basics. If you want to see any previous video, see any previous video.